So good evening everybody. This is The Science of Santa, which is a fairly trivial 25 minutes or so looking at whether or not Santa is compatible with the laws of physics. So that's the question I'm trying to answer. How many laws of physics does Santa break? And we know that Santa is, well, allegedly a portly, jolly fellow with a white beard and a penchant for wearing red suits. So although that does display questionable fashion sense, that doesn't mean he doesn't actually exist. So what about the claims that are made according to what Santa is capable of doing? He allegedly visits all households on Christmas Eve to deliver presents to all qualifying children. And qualifying means according to his naughty, nice list. And the question is, can we reconcile this rather incredible feat that's described there in just one sentence? Can we reconcile that with our understanding of the laws of nature, or basically the scientific method? And in particular, can we reconcile it with any of the science I've described in my other talks, which I'll just touch on now and again? So, as was mentioned earlier, I've got a few talks. This is about half of them, in which I'm talking about various aspects of astronomy, or how the universe works, or how we think nature works, whether it be quantum mechanics or general relativity or the Star of Bethlehem. And I'm going to draw on one or two of those talks to think about if they apply to our knowledge of Santa. So what we're going to do is to take this sentence here, Santa visits households on Christmas Eve to deliver presents to children. And we're going to deconstruct that and see which aspects of this actually break the laws of physics. So we'll start with how many children does he actually visit? So how many children get presents at Christmas? Well, we can't put a definitive number on that, but if we know that the Earth's population is about 8 billion or so, approximately 1/4 at the moment are under 18, so are classed as children, and of those perhaps 50% or so are eligible for Christmas presents. We're not going to get into an argument here about the religion of particular children or the religion of their parents. Let's just assume that Santa is very generous and will give presents to half of the children of the world. So that's about 1 billion children in total. And just for convenience, let's just assume that the naughty nice list is such that all children in the world are nice and none of them are on the naughty list. Okay, just makes the numbers a little bit rounder just to say 1 billion children. Okay. What about the next aspect of what we're claiming Santa does? Santa visits all of these children. So how does he get around? Well, according to the standard tale, he gets around by being pulled by flying reindeer. So we can ask the question, can reindeer actually fly? Well, we know that insects fly, and we know that birds fly, and we know that pterosaurs fly, though you don't see many of them these days, and we know that some mammals can fly. So what about reindeer? Well, if reindeer can fly, then apparently they choose not to do so for a lot of the time. Most of the time we're watching them, in fact. So there's very little evidence for flying reindeer. But I'm a scientist, and as a scientist I have to admit that absence of evidence is not evidence of absence. So just because I've never seen a reindeer fly, and perhaps you haven't either, that doesn't mean that they can't. So the jury is out on that one. We don't know whether they can or can't fly. But how fast must you go in order to deliver all of these presents? How fast could Santa and his sleigh actually fly? Well, if you want to visit 1 billion children, the number we came up on the last slide, if you want to visit 1 billion children in one night, and let's assume that's about 36 hours, in other words, you take advantage of going with the time zones during Christmas Eve, you fly around the world the right way such that you can visit each time zone and you gain a little bit more than 24 hours. But even in 36 hours, you'd still have to fly at about 2,000 kilometers per second. That sounds ridiculously fast, but actually it's only a tiny fraction of the speed of light. It's only 0.007 of the speed of light. In other words, if Santa is moving at less than 1% of the speed of light, he's in no danger whatsoever of breaking that particular speed limit, the speed limit that nothing can move through space faster than the speed of light. And that's covered in one of my talks called Fiat Lux, about the nature of light. Now, we know that no object can move through space faster than the speed of light, but that doesn't stop space expanding faster than that, so the expansion of space can be essentially as fast as it wants to be, which means some galaxies could indeed be carried away from us faster than the speed of light, and I'll say something about that a little later. So, aren't we going to end up with roast reindeer? If you move fast through the atmosphere, wouldn't the sleigh and the reindeer burn up? Just as a meteor or an asteroid entering the Earth's atmosphere, the air in front of the sleigh would compress and heat up. Some people say that moving fast through the Earth's atmosphere, the friction would heat things up. Well, strictly it's not the friction, it's the fact that when you move quickly through the air in front can't get out of the way fast enough and hence gets compressed, and compression produces heat. And we know that, for instance, from my talk on stellar evolution, where I talk about the ABC of how stars evolve, and the C of the ABC actually stands for compression, because compression produces heat, and hence when a whole load of hydrogen gas compresses, that produces heat, which ultimately switches on the stellar fusion process. So it does look like, if you try and move fast through the Earth's atmosphere, it would heat up. Now, even an aerodynamic sleigh will only offset that slightly. Even if you try and minimize the heating effect, you will always get compression of the air and it will heat up. So you should say to yourself, well, doesn't that mean that Santa and his sleigh are always going to be visible? Surely, if a great deal of heat is generated as Santa moves quickly around the world, wouldn't the sleigh be glowing white hot like anything else that we can choose? If I take this pen, at room temperature, it doesn't produce much visible light. But if I were heat it up to thousands of Kelvin, thousands of degrees centigrade, then it would glow red hot and eventually white hot. So doesn't that mean the sleigh ought to always be visible as a bright light in the sky? It should be easily visible. It shouldn't be something that we can hardly ever see. It should be absolutely obvious. Well, you could argue maybe it was. Now, it's a bit of a stretch to say that Father Christmas has been around since before Jesus was born. That's sort of getting the cart before the horse slightly. So maybe the bright light in the sky wasn't the Star of Bethlehem, but if we're trying to explain bright lights in the sky seen at night, well, there's plenty of those around. Again, a talk on UFOs. You don't see that many UFOs during the day. A lot of UFOs are seen as bright lights in the sky. So perhaps a bright light seen in the sky on Christmas Eve could indeed be the sleigh glowing white hot because of the heat generated. But as for most of what I've got to say here, there are alternative explanations. For instance, do we know anything about a particular type of matter that does not emit light, or does not absorb light, or doesn't reflect light? In fact, it doesn't absorb or reflect or emit any type of electromagnetic radiation. Indeed there is. It's called dark matter. So if Santa and his sleigh are made of dark matter, then even if it got very, very hot by moving quickly through the Earth's atmosphere, it wouldn't emit any light, because dark matter, no matter how hot it gets, will not ever glow white hot because it doesn't emit electromagnetic radiation. So if Santa and his sleigh are made of dark matter, that explains why we don't see this bright light flashing across the sky all during Christmas Eve. It also explains why Santa's sleigh doesn't show up on radar. If you think you've got an app that shows Santa's sleigh on radar as tracked by NORAD, well, I'm afraid you've got a fake app. If you imagine Santa's sleigh moving slow enough that it can be tracked by radar, there isn't any way that he could possibly visit 1 billion households in one night. So that app is a bit of fakery. Okay, let's come back to the claim. And let's pick out now households. We've said 1 billion children, and we've seen how Santa gets around with presumably flying reindeer in a sleigh that is allowed to heat up, because if it's made of dark matter, that's not a problem. But what about visiting households? How can Santa get down so many chimneys in one night? Let's put to one side for the moment the fact that a house might not have a chimney. If you want Santa to squeeze down 3,000 chimneys each second, which is what you would need to cover 1 billion households in one night, how on earth are you going to do that? The conventional picture of Santa is a rather rotund fellow who is circumference somewhat larger than most chimneys. So how could you possibly expect him to do that? Well, it's not actually impossible. We know from quantum mechanics, the talk I give about quantum mechanics is called The Weird World of the Very, Very Small. And we know from quantum mechanics that an atom is made of a nucleus and electrons and is mainly nothing. The nucleus is tiny and the electrons effectively have no size at all. If you were to replace the electrons with a somewhat heavier particle called a muon, and a muon can change into an electron, so there's no reason why an electron can't change into a muon, the result would be the atom is some 100 to 200 times smaller, which means Santa would be 200 times smaller. So instead of a jolly fellow of order a little less than 2 meters in height, Santa would be only about a centimeter or so in size, if he simply changed all his electrons into muons. Okay, I don't know how you do that, but that's irrelevant. If you were to do that, Santa would be this big and he would fall straight down a chimney, no problem whatsoever. That doesn't really help if there isn't a chimney in the first place. How do you get into a house or an apartment if you don't have a chimney? How can Santa get inside? Well, there's actually multiple ways that that could happen. One of them, if we come back to our saviour of quantum mechanics tells us that to go from outside a house to inside a house, you don't have to go through an open door or an open window. You can actually tunnel. It's a quantum mechanical effect called tunneling. You can actually go through a solid object like, for instance, a wall. A solid object like Santa can actually pass through a solid object such as a wall and get onto the other side. We've observed this many times for small particles. Okay, Santa is a bit bigger than a small particle, but if it works for something small, then in principle you can scale it up and say it should work for something large. So it does not break the laws of physics to say that Santa can get into our house without actually an open door or an open window, or indeed a chimney. So that's allowed according to the rules of quantum mechanics. Let's have a think about the timing. Santa does all of this on Christmas Eve, all in one night. How can Santa make so many deliveries all in one night? Well, even if travelling at relativistic speeds, which is something that we would allow according to the laws of physics, it would be tricky, but it's allowable. How could you do it in a mere 36 hours? Well, quantum mechanics once more to the rescue. We know that a particle, such as an electron or even an atom, can be in 2 places at one time. So if, for instance, an electron can be here and here simultaneously, then why can't Santa be in more than 2 places at once? So you're talking about him visiting 1 billion households, but according to the rules of quantum mechanics, he doesn't necessarily have to visit them one after the other. He can visit more than one house at the same time. Actually, this particular explanation also helps us for the previous one. Santa could, in principle, be outside a house and inside a house at the same time. That is not excluded by the laws of physics. And if it can be inside and outside the house at the same time, he can be inside multiple houses at the same time. So that has been proved for small particles, and there's no reason to think it isn't true of Santa as well. If you don't like that and you insist on Santa being only in one place at a time, then you would need an alternative way to make the delivery across 1 billion different households. If you insist that he visits them sequentially rather than all at the same time, then we'd have to find some other way of getting him to visit all of these places. How do you visit places that are all remote from each other quickly? Well, one way of doing it is to say, why don't you just distort space so that they're all close to each other? If Santa was capable of manipulating space and time, then it can explain some of his amazing feats. And one of my talks is about warping space and time, how mass distorts space and mass distorts time. So again, we know that is possible. How Santa does it, well, I don't know the details, but the idea of Santa manipulating space and time does not go against the rules of physics as we understand them. Let's look at the final aspect of that particular phrase, of Santa visiting households on Christmas Eve to deliver presents to children. And that is delivering the presents. How could Santa carry all of those presents when he visits all of these households? If we assume one present for each of 1 billion children, even if the present is quite small, that's quite a lot of presents. How could the sleigh hold 1 billion presents, even 1 billion small presents? Well, we've already said that we can warp space and time, so why can't you warp space and time such that the sleigh is bigger on the inside than it is on the outside? Again, that sounds weird and it sounds science fiction, but no, that's precisely what happens when matter distorts space. And the extreme example of that is a black hole, where if you think of a black hole and you draw a sphere around the black hole, the volume of the sphere inside is larger than the volume of the sphere itself. So it sounds a bit weird, it sounds very much like a TARDIS, it sounds very much like science fiction, but the idea of matter distorting space means that things can be bigger on the inside than the outside. So maybe that's one way that Santa generates enough space to store all of these presents. But if you don't like that, there's another alternative. We believe that we might be in a universe which has 3 dimensions, left, right, forward, backwards, up and down. But there are many people who believe that the number of dimensions of space in our universe is more than 3. Some people believe there are 10, or 11, or 12, or maybe more. So, all you would need to do is to move the presents from our 3 dimensions into one of these other spare dimensions, which exist alongside the 3 dimensions of space that we can perceive. Somehow, Santa has managed to access one of these other dimensions and he stores all of the presents there. Well, okay, maybe not. But we don't know how many dimensions there are. Just because we can only see 3 of them doesn't mean that's all there are. Maybe there are plenty more to play with. Yes, you might say, this is possible. This is not ruled out by the laws of physics. It is possible that Santa moves very fast and it is possible that he does these wonderful things. But surely, if we wanted him to do that, wouldn't that need a huge amount of energy? Well, yes, Santa and a sleigh and 1 billion presents all moving at relativistic speeds for him to get around the world, or perhaps a bit slower if he can be in more places at once at the same time. Still, it would need a lot of energy to allow him to achieve this on Christmas Eve. Well, if his sleigh had a black hole on board, that would not be a problem. A small black hole is enough to power, let's say, a starship to something close to the speed of light. So a small black hole would be enough to power the sleigh and to get it going around the world rather quickly in 36 hours. How big would that black hole need to be? Well, I don't think that black hole would need to be bigger than about, well, probably smaller than an atom. A black hole smaller than an atom would produce enough power to be able to power the sleigh with the sort of energy that we need to achieve the sorts of feats that I've been talking about. But there's another alternative energy source that we are completely overlooking. We don't have to go with black holes in order to think about an energy source that would be enough to power the sleigh. It's the elephant in the room. It's the one thing that we haven't yet thought about. What happens to all the mince pies? What if Santa could convert the mass of all the mince pies he's left into energy? E equals mc squared. What if he could do that? How much energy would that give him? How much energy would he then have to play with to power his sleigh and allow him to do these incredible feats? Let's actually just double check. If you don't like maths, look away now. 1 mince pie weighs about 50 grams, or strictly has a mass of about 50 grams. And if we say E equals mc squared and the mass is 50 grams, then we multiply 50 grams by c squared and we get the energy of 1 mince pie. 5 times 10 to the 15 joules. How many mince pies? Well, let's assume that not everybody leaves mince pies out for Santa, and according to the culture, some people might leave goodies or cookies or other things, but let's assume the mass is similar. If a few % of households across the world leave Santa a mince pie, then the total number of mince pies is something of order 20 million. 20 million multiplied by the number I've just given you gives you a total energy of mince pies of 10 to the power 23 joules. If he took all of the mince pies and converted them into energy, he would have at his disposal 10 to the power 23 joules. And I appreciate that physicists use joules, and to everybody else, you can't figure out what on earth a joule is, or a megajoule, or a gigajoule, or whatever. So what is 10 to the 23 joules in something more usable? Let's think about, for instance, a nuclear power station. Let's imagine a nuclear power station, the output running 24/7. A nuclear power station running 24 hours a day, 7 days a week, every day of the year, for 1,000,000 years. That's roughly how much energy that is. So you can see that a nuclear power station running for 1,000,000 years is a huge amount of energy, and that's what you could in principle get out of all the mince pies that are left. But how do you extract E equals mc squared from a mince pie? It's all very well saying the energy is there, and E equals mc squared is the exchange rate, if you like, between mass and energy. But how would you possibly extract that energy given a large number of mince pies? Well, one option is to take a mince pie and take an anti-mince pie and collide them together to release the energy. And you would do this, of course, in the Large Mince Pie Collider at CERN. But maybe that's not feasible because Santa wants to go around the world and he doesn't want to be tied to the fact that the energy is only output at CERN. He wants to have the energy wherever in the world he happens to be. So we don't want to restrict ourselves to only being at CERN. And of course the other problem is, yes, we have plenty of mince pies, but where do you get the anti-mince pies from? So you can't do this matter-antimatter collision to release energy unless you have the right amounts of anti-mince pies. So that doesn't seem to work too well. Is there an alternative way of extracting energy from a mince pie? Well, you can't necessarily extract all of the energy of a mince pie, but there is actually a very efficient way of extracting a large fraction, meaning perhaps a third, perhaps a half of the total amount of energy in a mince pie can be extracted. What's the most efficient way of extracting energy from matter? You might think that stars are quite efficient. If you take a large mass and put it at the heart of a star and undergo nuclear fusion, then that gives you enough energy to power a star for tens of billions of years. And you might think that sounds very efficient. But actually, fusion isn't particularly efficient, less than 1% efficient. The most efficient way of getting energy out of matter is to drop it into a black hole. So we've got black holes again. Maybe a black hole was already on the sleigh anyway. If you drop a mince pie into it, it'll release energy. We know that because, for instance, we see the result of dropping matter into black holes. Matter falling into a black hole can produce a quasar, a very energetic galactic nucleus. The matter falling into a quasar, well, it's probably not mince pies as far as we know, but the matter falling into a black hole can get converted very efficiently into radiation. It's so efficient that quasars can be visible from enormous distances. For instance, in a talk I give called Ancient Light, I describe how I photographed a quasar without using a telescope. This is just a camera on a tracker. I photographed a quasar which is on the other side of the observable universe. It's at a distance of some 25 billion light years. And it's moving away from us, it's receding from us at something like twice the speed of light. It's enormously distant and moving enormously fast. But it's so bright because of all of this matter falling into the black hole. It's so bright it can be photographed without a telescope from here on Earth. So we know that matter falling into black holes produces enormous amounts of energy. How much would a mince pie produce? I'm not too sure. I've tried researching this and I've looked it up, but I cannot find anybody who has studied the energy release of mince pies falling into a black hole. It's as if very few people have studied in this particular area of physics. So I can't give you a number, I'm afraid, but I'm sure it's large and possibly large enough for Santa. Okay, it's possible, and there's enough energy at his disposal to make this happen. But how could Santa actually do all this? Even if it's possible, according to the laws of physics, how can Santa manipulate, for instance, space and time to give him what he needs? Well, one thing to bear in mind is, who says that Santa has to be human? Why can't Santa be a little more like that? If nobody's seen Santa, everybody has to be asleep before Santa visits and leaves you presents. Everybody knows that. So maybe Santa has got green skin and big ears, and we only have a sort of a traditional view of what Santa should look like. So maybe that explains how Santa can manipulate space and time. Attempts have been made to see what Santa actually looks like. If you equate Santa with St. Nicholas, then St. Nicholas was a 4th century Greek bishop, and facial recognition of his skull and the assumed tissue depths, much like a forensic reconstruction, that is what we think St. Nicholas looks like based on his skull and tissue regeneration. That was done by a laboratory in John Moores University. So maybe that's what St. Nick looks like, and if you equate the two, maybe that's what Santa looks like. But of course, our traditional view of Santa is just a little bit different from that. But we're not convinced whether he has green skin or big ears. So, coming back to the original question, is Santa compatible with the laws of physics? How many laws of physics does Santa break? I think the answer is none. So feel free to draw your own conclusions about the existence, or otherwise, of the portly, jolly fellow with the white beard and the penchant for wearing red suits. Regardless of your conclusion, I would like to wish you all a very Merry Christmas. Thank you for listening.